All right, for today's lesson, we are going to pretty much exclusively be dealing with tangents on circles. All right, we've talked about tangents before. We've talked about points of tangency, which we'll go over again real quick here in our notes. So a tangent line is in the same plane as a circle that intersects the circle at exactly one point. So in other words, it can only hit the circle at one point. It can't go through the circle because that'd be a secant line. It can't be within the circle because if it's only inside the circle, it could be a chord or a diameter or something like that. Will only hit the outside of the circle at one point. And that point is called the point of tangency. And so as you can see with the notation here, that line AB right there, and you know it's a line because it has the double arrows on top of AB, is tangent to circle C. This little symbol right here means circle C at the point A, right there. And that's what we call that point of tangency. And AB without the arrows, AB with only one arrow, which is a ray, or AB with two arrows, either way you want to look at those, any of those things are called tangents because they all would hit at exactly that same point A of tangency. A common tangent line or ray or segment that is tangent to two circles in the same plane is also going to be something that we're going to talk about. So in each one of the figures below, line L, and you can see they're both labeled with a lowercase l, is a common tangent of the circles F and G. And there are different ways that this can happen, which is why there's two diagrams. So if you see the first diagram, the one on the left, the circles are separated. And that's important because it means that you can actually have more than just what you see there for line L. Line L is a tangent line which is common to both of them. So they call it a common tangent because it hits circle G right there. And it hits circle F right there. Draw a slightly better circle there, right there. And it only hits each one of those circles at one point. Well, there are actually three other common tangents to those two circles. What you might want to do is see if you can figure out what those common tangents might be. So if you want to pause this for a second, see if you can figure it out yourself, probably be a good idea. All right, if you've paused it and you've taken a look, let's see if you figured them out. I'm going to erase those circles here real quick. So there is another common tangent, which goes between F and G, which basically kind of crosses line L and looks something like this. Let's see how well I can draw this. It'll hit right there, and it'll hit right there. So I don't know, we're not going to really label that line specifically, but it's going to hit right here, and it's going to hit right here. So there is another common tangent. So basically there's an X that crosses in between those two. Okay, this works when you have separated circles. There are actually two more. I wonder if anybody figured these out. I can also have a tangent line which hits only each one of the circles only one time if I think about it on the top and the bottom of the circles. So I can draw a tangent line. Again, we'll see how good I can do this, which hits circle F at one point and then circle G at one point. So like right here and right there. Excuse me. And then if you think about it, there would be something similar to that on the bottom as well. So might hit F here and G right there. Did my best to draw the straightest lines I could. Kind of missed F a little bit, but you get the idea that if you laid it right there, it would hit those two. So there's actually four common tangents when you have separated circles. You can almost always have four. You kind of have that X in the middle, and then you have one on top and one on the bottom. When you have two circles which are touching each other, like the ones on the right-hand side, You have that one tangent line L, which basically goes right in between F and G and hits right at that one point where F and G, the circles, actually touch each other, right there. And then, just like the previous ones, you're going to have the exact same type of thing. You're going to have one on top and one on the bottom that hits each one of the circles. So you might have one that looks like this on the top. And again, that's only supposed to hit at one point there, one point here. And then you'll have one that hits the bottom, which hits like one point there and one point there. My lines are getting awful. I apologize. Those are not really good lines. But hopefully you understand the idea there. So again, a tangent must hit the circle at only one point. If you have multiple circles, you can have common tangents. If you have two separated circles, you'll have four common tangents. You have the X in the middle, and then you have the top and the bottom. If you have two circles which are touching each other at that tangent point, you'll have the one line that goes right in between the two circles and hits at that common tangent point, and then you'll once again have the top and bottom. So that's your basic idea with tangents and circles. So let's take a look. It says to copy each figure. You don't have to. You should have it on your page. But then draw the common tangents. Now, it says if no common tangents exist, state that no common tangents exist. The first one that they give us is slightly different than what we've seen already, because that one, the two circles actually intersect each other. So in this case, you can't have the one that goes in between the two circles because the two circles actually kind of crisscross. So that's not going to work. The only ones you're going to have are kind of the ones on the top and the bottom. So you're going to have something which hits the big circle on the bottom and then hits the little circle on the bottom, something like that. So you'll have the tangent point here, point of tangency here. Again, you can't have anything that goes in between or through the middle because that would cross through too many points. So the only other one that you can have is the one that's going to be on the top. So it'll be much more of a steep angle here, but it's going to look something like that. And if you have a straight edge, you can certainly line your straight edge up there to see exactly how those things would hit. And then on the second one, it tells us here, it says these circles are going to have four common tangents. That's the separated one. That's the one that we did before. So you're going to basically have your X in the middle. Again, seeing these isn't exactly easy. So if you have a straight edge, line your straight edge up. Oh, that was horrible. Let me try and redraw that. Line your straight edge up if you can. All right, close enough. Only supposed to hit one point there. Supposed to have the X, so it means it's going to hit a point like maybe here, coming up to there. And then you're going to have the top and the bottom. Let's see how good we can do with that one. Man, my lines are just horrible. But the concept should be there. And there you've got your four common tangents. All right. So we have this theorem, and the theorem says that if a secant and a tangent intersect at a point of tangency. So this one is your secant right here, and this one is your tangent because it hits at only one point. The secant line hits through 2 points and keeps on going. They both meet at point F. So that's what they're talking about. If a secant and a tangent intersect at the point of tangency, so at the outside of the circle, then the measure of each angle formed is 1/2 of the measure of its intercepted arc. So in other words, the angle which is, let's use this color, the angle which is in here is going to be 1/2 of the arc that this thing intercepts. Well, it intercepts the arc between F and G. So from F to G is where this angle is. And the arc is right there. Whatever the measure of that arc is, the angle in blue is half of it. Or, likewise, we could also do the major angle out here, the major arc, although they don't give us a third letter, so you can't really call it that, but whatever that arc is out there, this angle is going to be half of that arc. So I'll just put example numbers in here because this isn't exactly what it is, but let's just say that this arc, we'll say that arc FG measures 60 degrees. So if we say that this is 60 degrees, then our angle HFG, angle, try and write that correctly, HFG is going to be half of that. So it's 30. Okay, likewise, if we knew that the arc between F and G is 60, then we know that the arc way out here, because it has to add up to 360, has to be 300. That means that the angle that's formed right here in red would have to be half of that, which is 150. And let's see if that actually makes sense. If this angle right here is 150 degrees, and the angle that we just measured for HFG is 30, well, these two things combined should add up to 180 degrees since they're sitting right on the line, and 30 and 150 definitely add up to 180 degrees. So that works. Again, so what this works for is if you have a secant line which intersects a tangent line at a specific point, then whatever the arc is for the intercepted secant line, the angle in between is going to be half of that measure. Okay, let's see if we can do an example here. In figure, AB is the tangent to the circle O at the point T. So T is your point of tangency. Says that the measure of CT, that's this arc right here, is 110 degrees. They want to know what the measure of angle CTA is. Well, that's this one. It's not the one that was inside, it's the opposite one. We can do this in one of two ways. Either we can figure out what the remainder of the circle is and cut it in half, which is probably easy enough to do. So we can figure out the rest of that, or we could figure out what this angle is and then take it away from 180 since the other one has to be supplementary to it. Doesn't matter, either way is going to work, and we'll show it both ways. So if we want to find the missing arc, the big one, 360 minus 110 should be 250. And then if you cut that in half, the measure of angle CTA would be half of 250, which is 125 degrees. Now let's see if that works the other way. If I wanted to find the measure of this angle right here, well, that's going to be half of the 110. Half of 110, so the measure of angle, we'll call it CTB, is going to be 55 degrees. Write that so it actually looks like a 55 degrees. And then you do 180 minus 55, which indeed gives you 125 degrees, which is that angle right there. And that's the one that we found over here. And again, either one of those ways work. It just depends on which way you see to do it. So there's no right or wrong way when it comes to doing that specific problem. Whoops. Okay, so let's do the next example. Determine the measure of angle DBC. So we are looking for this one. And what they gave us here looks like they gave us this arc. So if I'm looking for the other angle, again, I could either figure out what half of 73 is to fill in the angle right here, or I can figure out what the difference between 360 degrees and 73 is, and then take half of that, and we should have our angle. I think that might be the easier way to do it. So 360 minus 73, what's that going to be? 287, I believe. You can double check that just to make sure. I'm pretty sure that that is correct. So that is this whole piece. I just used green to go over in green. That's probably not a good idea. That's that whole piece out there. That's 287. So then the orange arc, the orange angle that we're looking for there is half of that. And whatever half of 287 is, 287 divided by 2 should be, what is that, 143.5, I believe. 143.5 degrees. That is the measure of angle DBC. And that's the one we're looking for. Okay, a few more. We want to determine the measure of angle BCD. BCD, again, that's this big one over here, but they gave us the arc over here. So let's do this one in a different way. I'm going to find the measure of this angle, which I know is going to be half of that arc. So the angle that we have here is going to be 44 degrees, because that's half of 88. So then to find the measure of the angle we're looking for, well, that has to be something which adds up to 180. So 180 minus 44 is going to be 136 degrees. So the measure of angle BCD is 136 degrees. Okay, and just a completely different way of doing it. Okay, and on the next page, there are 3 more. Why don't you guys, if you can, go ahead and give those a try, pause the video, and then come back to it after you've given it a shot, and see if you can figure it out. I do need to add one thing in there for you before you do that, however. I need to give you that this piece out here is 260 degrees, because that second circle didn't give you any information. So we're going to tell you that arc over there is 260. All right, give it a shot and see if you can figure them out. Come back and we'll look at it. Okay, if you've had a chance to give it a shot, let's see what we came up with. So they want, in the first one in the upper left here, the measure of angle BAF. Well, that's interesting, considering that there is no F. Maybe I should have added that in there too. Typos, apologies. We're going to put the F right there. So if you weren't sure about that one, apologies. We are looking for that angle right there. So I don't know. Let's do half of the angle that they gave us, which is going to give us this piece right here, which should be 62. And then I know that 180 minus 62 has to be the one that we're looking for, which should be 118 degrees. That's going to be the measure of angle BAF. Okay, let's try the upper right one. We are looking for the measure of angle ATC. Oh, this one should be much easier, because that is literally just going to be half of our 260, which is 130 degrees. And then the last one down here at the bottom, Measure of arc, AEB. So we're looking for something different. So we are looking for the measure of the arc between A, E, and B, which is this arc right here. So that's just going backwards. Well, they gave us the measure of the angle is 133, which means that instead of cutting the arc in half, we have the angle, so we're going to double it. So the measure of that arc should be double 133, which is 266 degrees. All right, we are going to come back with a second video, also based upon tangents, and that should finish up the lesson.